Okay, before we start, does anybody have any questions on the Snell's Law quiz that I just handed back? Is there anything that's not clear? One thing I did notice when I was grading it is on this third question, and most people just plug one in anyways, which is fine, but I forgot to give you the wavelength. So I asked for what is the wavelength of velocity of the light inside the glass block. So basically the velocity and the wavelength are velocity in the vacuum divided by the index of refraction, which comes up to 2.07 times 10 to the 8th meters per second. And the wavelength is whatever the wavelength is divided by the index of refraction also. So a bunch of people plugged in 633 nanometers, which is what the helium neon laser wavelength is, which is fine. So if you did that, that's cool. If you just put wavelength divided by index of refraction, that's fine also. So apologize for that typo. All right, so when I left you last, we were doing the thin lens equation. Don't know if you've had a chance to do any homework problems, but we will have a lab today and Thursday, which will give you lots of experience in using the thin lens equation to validate your experimental results. But basically, just to pick up where we left off last class, the thin lens equation is an approximation that we use to identify where an image is being formed. Just to refresh your memory, if you look at the schematic on the screen here, if you have a lens, a positive lens, okay, it has a positive focal length. The object distance is the distance away from that lens. Okay. That distance, if it's to the left of the lens using the Cartesian coordinate system, has a negative number associated to it. So if I put something 30 centimeters away, it would be minus 30 centimeters in the equation. When you calculate where the image is being formed, the eye is the image is formed, in this case, to the right of the lens. Any distances to the right of the lens are positive. Okay? If I show this as being upright, above the optical axis here, and this has a positive size to it, so if we're looking at whether it's upright or inverted, in this case the image is inverted, so it will have a negative magnification, calculate magnification. So I do have a short quiz that we're going to go hand out at the end of class today. It's going to be due Thursday, just to make sure everybody is comfortable with the thin lens equation. Again, you're going to beat this into the ground in lab, so I'm sure you'll have no problem with it. We've looked at what happens when you take an object, okay, and you move it from way over here. What happens to the image as you move the object closer? Okay? As I take if I take an object and I put it really far away, the image will be kind of the inverse of that. It'll actually be closer to the focal point and smaller. The closer I move that object to that focal point, the farther and farther away the image will be formed, still inverted, but growing in size. And you'll get a chance to do this actually in the lab today. Special case, what happens when I put that object right at the focal point? Where does it come to focus? Where does the image get formed? Infinity. Okay. And I can show you that mathematically. I mean, again, this is why we like equations. So if I take that thin lens equation and I solve it, so I got 1 over d0 plus 1 over f is equal to 1 over di. Okay. What if I make this object distance equal to the focal point, right? If d0 equals f, because it's minus, I get 1 over minus f plus 1 over f is equal to 1 over di. What's 1 over minus f plus 1 over f? 0. So I get 0 being equal to 1 over di, and if I go and solve for di is equal to 1 divided by 0. What happens when I divide a number by 0?
0.
You can't divide by 0.
Who's right?
You can't divide by 0.
0.
Mathematicians will tell you that it's undefined, okay? Because you divide anything by 0, theoretically, it's infinite, which is undefined. It's like way, way out there. You can't measure it, okay? Engineers actually can define 1 divided by 0. What happens when you short out an electrical circuit? Things blow up. They actually call those poles and zeros if you go through electrical engineering, but the things blow up when you divide by 0. If you look at current, remember Ohm's law, is equal to voltage divided by resistance. Well, if I've got, take a 9-volt battery, okay? Like 9-volt battery, I've seen this happen before. 9-volt battery, and you place a wire from the positive to the negative. Or 9-volt batteries have both terminals on the same side. If you ever throw one of those away or throw them in the trash, always put a piece of tape over it, because if it hits a piece of metal, it will blow up. I've seen it happen. There was one guy in my class a few years ago walking down the hall, his backpack, and all of a sudden you hear this boom. It's like, what the hell is that? And there's smoke coming out of his backpack. He's like taking the thing off really fast. And sure enough, he had a 9-volt battery in there, and it hit something metal in his backpack, shorted out, and blew the battery out. But basically, what is a short circuit? A short circuit is 0. 0 resistance, right? 9 volts divided by 0 blows things up. It's not theoretical. It gets hot. So anyways, going back to the optics, this means that the image is formed at infinity. Okay? Meaning that it never comes to focus. It just keeps going and going. Okay? So you take this object, you move it towards the focal point, the image gets farther and farther away, and gets bigger and bigger and bigger. Okay? You hit this point, and it never comes to focus. Okay? You can never image it. And then as you move past that point, when you're between the lens and the focal point, what happens to the image? It becomes negative. I mean, the image distance becomes negative. It takes this image and flips it around to the left side of the lens, okay, and it turns it upright, okay, and it's going to be bigger. The magnification actually becomes positive, and what happens is you form a virtual image. How do you see that image? You can't project it onto anything anymore, right? But you can look through the lens and actually see it. And what you look at is a magnified version of the original object. And that's basically a magnifying glass. And you will do this in the lab today. So just some of the nuts and bolts. If you have, magnification is always either the image distance divided by the object distance. This is where the signs are important because it tells you whether the image is upright or inverted. If your object distance is negative and your image distance is positive, you basically have a negative number, which means the image is going to be upside down, it's going to be inverted. If it comes out positive, like in the case I just explained with the magnifying glass, both the object distance and the image distance are negative. You divide 2 negative, you get a positive, and the image turns upright. Did a couple examples of this. Then we looked at multiple lens systems. If you take 2 lenses, positive, negative, positive, positive, negative, positive, doesn't matter what the combination is. If you have 2 lenses in your system, how do you analyze this? How to do this? One at a time. You treat each lens separately. Forget about the other one. Okay? The image that's formed by the first lens, you treat the first one first. Okay? Image that's formed by this one serves as the object for the second lens. And sometimes this screws people up a little bit, because sometimes in this situation, for example, I may have an object over here, okay? And if I move it close to the focal point, that object will form an image that might be beyond the location of the second lens, okay? So what happens if my image from my first lens creates an image over here? The object, my first lens, creates an image that's beyond the second lens. Then you, again, when you treat the second lens completely separate, all you have is an object now that's on the right side of the lens, and all that means is that the object location is now positive. Okay? Apply the same equation, thin lens equation, treat it separately. Wherever it comes out, it comes out. If you calculate the size or the magnification of each lens. Okay? This is going to create an image that may be over here somewhere. It's going to have a certain size. Again, if that's the object, that's the size. Okay? So you start off with that size and then use it for the second lens as an object. Or if you can calculate the magnification of both of them, if you multiply the two magnifications together, you get the overall magnification of that optical system. So you can play with it and manipulate it however you want. But the takeaway from this is just treat each lens separately. Okay? And you can do some interesting things. There's actually a question on the lab today, or the write-up part of it, that asks you, for example, if we look at one of the things we're going to do in lab, we're going to take a lens, we're going to put an object behind it, okay, and you're going to measure where the object comes into focus, the image comes into focus. And then you're going to take the object and you're going to move it closer and closer to the lens until you get inside the focal length. Okay, in which case you're no longer projecting a real image, you now have a virtual image. Well, virtual image, you can't take a ruler, and look inside the lens and try to measure how far away it is. It doesn't work that way. Okay? You can see it. It appears to be bigger. It appears to be a certain distance away, but there's no physical way of measuring that, unless you use your imagination, take a separate lens, and then put it after your first lens, and you can actually create a real image. You can basically use the virtual image of the first lens as the object for the second lens, and you can project that image to create a real image that you can actually measure, and then just back calculate using the thin lens equation what the actual size and physical distance is behind the first lens. But you can measure it, which is cool. Of course, I just gave you the answer. That's a nice guy. Okay, so we did a bunch of examples with multiple lens systems. Had you guys do one. We talked about different aberrations. We talked about spherical aberration, which is the imaging limitation based on the fact that we're humans and we can't manufacture optics that are perfectly spherical or perfectly to the right prescription. Ask the people who built the Hubble telescope. But spherical aberration can be corrected by closing down the aperture, basically limiting where the light goes through. If you shrink down the aperture so that light only goes to the central portion, it tends to be more forgiving, because usually the aberration is due to the outer portions of the lens. We looked at coma. Light comes through a lens at an angle. Does it come to a spot? Is the image elongated? We looked at astigmatism, which is light in one axis versus the other come to focus at different spots. Then we looked at chromatic aberration, basically different colors coming to focus at different spots because of the variation of the index of refraction due to variation in wavelength of light coming through. Which leads us to collimators and beam expanders. So when we come back from spring break, the first lab we're going to do is build a Keplerian beam expander. Okay? And these are used to expand beams. Anybody remember why we like to expand laser beams? There's a reason for it.
Because it's easier to focus.
Yeah, not easier, but you can actually focus it to a smaller spot. Okay, the spot size is, and I'll throw an equation up there, so there are equations. There's an equation that says spot size, how small can I focus a laser, equals, this is for a Gaussian beam, which we'll get into, but 1.27 lambda over d, okay, times the focal length of the lens. So if I have, a 10 centimeter focal length lens, and I know what the wavelength is, the spot size is inversely proportional to the diameter of the beam. So if I start out with a beam that's a certain size, okay, this is d here, depending on the wavelength, the bigger I make this beam, the equation, the smaller the spot size gets. Okay? Or the shorter I make the focal length, the smaller the spot size gets. Or the shorter I make the wavelength, the shorter the spot size gets. So there are three things that contribute to how small can I focus this little spot of light. Okay? You guys are all you all have like Blu-ray players, right?
Yeah.
Okay, remember the old DVDs that were not Blu-ray, they were not HD, but basically just, they used a red laser. Why can you get HD out of a Blu-ray?
Because the spot size is smaller, the density of the platter.
For the same size disc, if you shorten the wavelength from red to blue, okay, it's a squared relationship between the wavelength and the spot size. So when you shorten the wavelength by using blue light, you can fit a lot more information, a lot more spots, and little holes in your DVD player, which means you get a lot more in there, which means you get HD. When you are trying to send a laser beam to the moon, okay, think about that for a second. If you're trying to, and forget the focal length there, if you remove this, okay, this equation then becomes the divergence. You know, how much does a laser beam spread out as it travels through over a distance? If you just use this equation, 1.27 lambda over d, that defines, that's the equation for the divergence. So if I want my beam to spread out less as I'm shooting it at the moon, okay, what do I have to do?
Blow it up.
Make it bigger, right? The bigger the beam, the straighter it's going to go. The straighter it goes, the less it's going to spread out. The less it spreads out, the more energy that's going to hit the moon that can reflect back off the retroflectors to come back and be detected. Everybody saw the Big Bang episode, that episode, right? They're on the roof. Penny brings her boyfriend up there. You're going to shoot a laser at the moon? You're going to blow it up. But they actually were demonstrating something very cool. You know, they pulsed a green laser, which was probably a frequency double the ag laser, diode pump. They sent it up, they sent some really rapid pulses of light, and they sat there and waited. They counted how long it took for that beam to come back. And basically it's a time of flight, it's laser radar basically. You know, how long does it take for the beam to go back, and calculate how far the moon is. But what do you think the wavelength? Is there an issue, like if you're going to shoot something at the moon, what is the importance of the wavelength? Is there an importance to the wavelength?
Well, it has to travel through a vacuum.
Well, before you get to a vacuum,
It's gotta go through the
you gotta go
atmosphere.
through the atmosphere. So even though they were using a green laser, which is fine, I believe the first Apollo mission used a pulse ruby laser, which is red. But there are better ways to do it. I mean, if, you know, depending on how much absorption in the atmosphere, there are certain windows of transmission in the atmosphere, 2.9, around 3 microns in wavelength, that's the lowest absorption of the atmosphere. So if you really want to do it with minimal loss, you would just do it in the infrared. But, you know, you use what you can. So, but that's, you know, these are design equations that give you good approximations for modeling optical systems. So in this Keplerian beam expander, okay, there's a different variation called the Galilean beam expander that uses a negative lens. And what do you see is there any difference between those? I mean, one uses 2 positive lenses, one uses a negative and a positive lens. Any issues with that? Why would you use one over the other?
Well, I mean, with the Galilean one, it looks like you're actually bringing the image back so you can focus it.
I mean, the goal is you take a smaller beam, you want to spread it out, and then collect it and recollimate it, straighten it back out with a second lens. And both of these do that. This one just brings to a focus and then diverges the beam and expands it back out. This diverges the beam right from the get-go. Which one do you think? And I don't expect you to know this because we haven't gotten into wave optics, it's a portion of the class yet. But in the first one, if you were trying to expand, let's say, a high-powered carbon dioxide laser, you know, you want to basically grow make the beam bigger, expand it so that you can focus it, you know, do materials processing. It doesn't have to be a CO2, whatever high-powered laser. If I bring that laser beam to a focus, okay, do you see any problem with that? Even if it's just in air? You never seen a laser pop the atmosphere? Ionize the atmosphere? So if you take a high-powered laser beam and you focus it down, you can get enough energy concentration there where you actually ionize the air. You basically create a spark in air. Where do you see that? Lightning. You create a little lightning. And it actually sounds like a shotgun going off. It's like boom, boom, boom. But, you know, in some applications, For example, they use a laser called a T laser, transverse excited atmospheric pressure, TEA laser, at the Heineken beer plant in Holland. And they do this, they basically take a high-powered laser beam, they pass it through a template that has the barcode on it, okay? And then they image that using the thin lens equation, by the way. They image the barcode all at once onto the can, but the laser is powerful enough that even though the barcode is like that big, they can burn it all at once. And they use a T laser to do this, but in order to image it, they have to use a positive lens. So as these beer cans are flying down a conveyor belt, this laser is going boom, 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 boom. It sounds like a machine gun going off. And all you see is this green blur of cans going by. You can't see the cans are moving so fast, but it's like boom, 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 boom. Pretty cool. But you can hear the laser. It's not the laser itself that's making the noise. It's the ionized atmosphere from focusing it and imaging it that's making the noise. Sometimes that's good. Sometimes if this is, you can get the same, you can do the same thing with mirrors too. If you have two curved mirrors that can bring the light to focus, like in the center of a confocal laser. Again, we'll talk about this later. But if you bring it to a focus, you do get that ionization, and sometimes if that happens to be in a crystal for a solid state laser, that can cause problems. Okay? So in some applications, that's a problem. On the other hand, you might be like, well, why do it at all? Why don't you just use this? The good thing about this is for lower power applications, when you bring that laser beam to a focus, at that focal point, that actually has a lot of good information. If you want to clean up a beam, this is another lab we're going to be doing when we get into the wave optics portion of the class. But if you bring a laser beam to a focus, if you have a scratch on your lens or a dust particle, when you pass light through it, it's going to come to a focus, but it's going to, the scratch itself is going to diffract, it's going to bend off axis. So if you don't want that light to be included, in your beam, because it looks ugly, right, Dave? And when you expand the beam out, you get all these little interference patterns, squiggly lines, and you want a nice clean beam of light. You can just put it through a little pinhole filter, block out the diffracted light, let the beam expand. When you look at it again, whatever aberrations happen to be, scratches, whatever happen to be on your optic, can be physically removed. You can filter them out, basically. So, and you will do that in a few weeks. And actually, when we build this collimator, so it's actually part of that lab. So, this one here, don't have to worry about that because you're expanding the beam right away. So if you have a high-powered laser and you don't want to get the ionization of the atmosphere, pass it through this, spreads out right away. The only problem with this is you don't have the ability to filter that, whatever aberrations may be out. But in most high-power applications, you don't really care because the beam is supposed to be there to burn holes in things, not to be used for interferometry and any very sophisticated measurement work. So it all depends on the application. All right. So, we may do this, we have time on Thursday, we may actually go through do some ray tracing. You don't have to use the thin lens equation, or any other equation for that matter, to figure out where an image can be formed if you have the dimensions of your optical system. If I have a lens that's a physical lens, let's say it's 25 millimeters in diameter, okay? I know what the focal length of that lens is. I can graphically determine, get a piece of graph paper and a ruler, and figure out where the image is going to be formed using something called ray tracing. For example, if I show my lens, and this can all be done on a piece of paper. If I show my lens, you can actually draw it to scale on a piece of paper. If I draw an object a certain distance away, okay, if it's to scale, you can do this. With 3 lines, I can determine where that image is going to be formed. We have 3 lines. One's a parallel ray, one's a focal ray, one's a central ray. From the top of your object, if I come straight across, just draw a line, hits the lens, and it comes through the focal point on the backside of the lens. If I take another line, draw it right through the center of the lens, okay? Then I take a third line, and I draw it through the front focal point of that lens, and then have it diverge, or come out collimated. Where these 3 lines intersect, that is where your image is going to be formed. Pretty straightforward. These are pretty accurate. And again, if we have time on Thursday, we'll do this.
So you can only figure it out with just 2 of them?
You could figure out with just 2 of them, but
the angles are set.
yeah. The graph paper is the best way to do this because you can trace the line, follow the lines and stuff.
Yeah,
But it's amazing. It's actually extremely accurate. I actually, when I go through this exercise, I give some graph paper and have you do it. And then we calculate for those parameters using the thin lens equation where the image is going to come out. You usually come out within less than 1% error. You know, it's just based on how thick your pencil is when you're doing it. But it actually comes out pretty accurate. So there's other, you know, if you use a thin diverging lens, same approach can be used for that. You just take your line, do it the same way you would for a positive lens, except, you know, when your lines diverge on the other side of the lens, you just trace them back. So this line comes out, we go like that, okay, and then we trace it back here. This one here goes through the second focal point, okay, trace it back here. This one goes through, I think this one's actually, this is the wrong one, actually. Anyways, the two focal, oh yeah, it comes to the focal point here. So the third one comes out this way through the center and gets traced back this way. So basically you can where the lines intersect, that's where the image will be formed for a negative lens. So basically it's the same thing as the positive lens, only when you draw the lines coming out, you have to follow them back to their origin. So you can do it for both types. All right. So today, what I'd like to do is switch gears and talk about mirrors. Okay? Now, just when you think you've got your arms wrapped around how lenses form images and where the image is going to be formed, somebody goes and throws mirrors up here. And so it's a double-edged sword. Mirrors, just as easy to analyze as lenses, and they actually use the thin lens equation exactly the same way as you would for analyzing a lens system. Applies to mirrors as well. The only thing is, with a mirror, it's backwards because light's going into a mirror, but then it's reflecting back. So you do everything the same way you would for a lens, but wherever your images are formed, it's the opposite of a lens. Okay, so if your image distance is positive image distance of a lens, it will be on the right side of the lens, right? Right? Yeah. So how do you measure that if you're in the mirror? You don't. You're behind the mirror. So the images that are formed on the right side of the mirror are actually virtual images. The images that are formed on the left side of the mirror are actually real images. So you just kind of think, you do it exactly the same way as you would for a lens, except when you come up with your answer, if you get a real image for a lens, that's actually a virtual image for a mirror. Yeah.
How does the one-way mirror work, the window?
Anybody know?
Depends on one room being darker.
Yeah. Yeah. Two-way mirrors are nothing more than pieces of glass that have a slight reflective coating on them, and depending on which side of the mirror you are, if the light is brighter, okay, then it'll allow you to see one direction. Perfect example is like in your house, right? In the daytime, because it's really bright outside, what's happening? The sun hits the window. You can have the lights on in the house, but in the daytime, it's very hard to see into your house because you get a 4% reflection from the outside. That 4% reflection from daylight actually is a lot stronger than the light that's in your house. So you get more reflection off the surface, and what you get is just a reflection off the glass. All you see is the glare. At nighttime, there's no light outside. All the light's coming from inside, so whatever you see, you can see right through it. So actually, your window in your house is kind of like a two-way mirror, depending if it's daytime or nighttime. So you ever go to the Springfield Science Museum? They have, I think, where is it? It's in the basement part of it. But they have like a two-way mirror. And one person sits on one side, one person sits on the other, and you can adjust the light levels on both sides. And if you dim one, increase the light on the other, okay, you're looking at this, so you're seeing a reflection of yourself, but as the other person increases their light, you're seeing more and more of them, and you can basically put your two faces together and kind of morph them. It's kind of freaky, but fun at the same time. But that's an example of a two-way mirror. Yeah. So, mirrors. What do we use mirrors for? Well, most of the answers are obvious, but mirrors are used for reflecting light. The mirror you look at in the morning every day. But you also have curved mirrors, concave mirrors and convex mirrors. Concave mirrors, okay, if you have a mirror that's concave, where do you see that? What's that? At a carnival, yeah, it'll distort your image if it's kind of wavy, but anybody have a bathroom mirror? One of those makeup mirrors, but in the hotel, you know, you have the mirror that's on the wall, and you look at it, and it blows up all your pores and makes it, you know, look pretty ugly. You see all the hair in your ears and stuff. Those are concave mirrors. Okay, magnifying mirrors are concave.
Headlights? Headlights have.
Headlights, I believe, are parabolic. They're curved, they're concave, but they're parabolic, so the light gets generated in one spot, hits the mirror, and then gets collimated or divergent, depending on you know, what the angle is. But usually those are parabolic. Convex mirrors, and this is a convex mirror. Okay, where do you see these? Every time you look at your side view mirror, okay, images are closer than they appear. Okay. Concave mirrors are magnifying mirrors. They actually make objects look bigger. Convex mirrors actually do the opposite. They make the object look smaller. So if you're looking in your side view mirror and the car behind you on the side view looks smaller, it actually isn't farther away. It's just the illusion that it's farther away, but it's actually closer than it appears, because it actually has like a magnification usually that's less than 1, so it makes the object look smaller. For seeing around corners, you know, banging people. Mirrors are used for a variety of applications. You can use mirrors for spreading out laser beams. How do you expand the laser beam? You know, we were talking about, you know, the shining the laser on the moon. How do they do that? How do you expand, you know, a high-powered laser beam? How does a telescope work? Reflecting telescope. And basically a beam expander and backwards. So if you look at a reflective beam expander, okay, what you would take is a concave mirror, okay, and a convex mirror. This is a convex mirror. This would be the concave mirror. Okay, and if you take a smaller laser beam, pass it through a hole in the center of the spherical mirror, what's going to happen is you're going to get light reflecting off of the positive mirror, being collimated or focused with the negative mirror. So you could take a little laser beam like this, small b, and make it a big beam like that. Okay. The cool thing also is, and I actually worked on one of these back in the 80s, remember Ronald Reagan, Star Wars, laser space kind of thing. Big ones that were like the size of this room big. But mirrors are nice. They're better than lenses for the only reason that they're easier to make. It's hard to make a lens that's like huge. Heavy glass, I mean, just the polishing. Not so hard to make a big reflective beam expander. Yes?
After that process, does the laser still keep its intensity?
Well, the energy's still there, it's just spread out. And what happens here, if you're trying to, you know, this is, it's basically a reflecting telescope. Light comes in, does the same thing backwards. But it depends on what the goal is. If you're trying to hit the moon so you can reflect light back, you want this to be collimated. One thing that they do is they make adaptive optics or deformable optics that you could put a little pressure on the mirror here and here, little actuators that can squeeze the mirror. If you do that, it focuses it. You know, and this is what we were doing in the Star Wars program. That focus was set on a missile. So you take a large, let's draw the whole system for you. So you take a big ground-based laser. This is the one I work at anyway. You shoot it up into outer space, okay, through the atmosphere at a wavelength that is absorbed minimally. Okay, reflected. This whole thing is contained in a satellite. Reflected off a small mirror, pass it into your beam expander. Okay, target this and figure out where the target is, and then apply pressure on parts of the mirror to focus it. You can do that really fast. So that's kind of cool. You know what the cool thing about this is you can take that same system, make your beam really big. Remember, the bigger the beam is, the smaller you focus it. Turn this thing around, miniaturize it, which is what they did at Boston University's Photonics Research Center. When you drive down the Mass Pike right across from Fenway, there's a nice shiny building that says Boston University Photonics Center. But they use this for manufacturing. For, you know, how do you create the masks for doing photolithography for very small semiconductors? Well, you make the bigger beam, you focus it down to a spot, and if you use adaptive optics, you can actually manipulate the phase profile, which is, again, we're getting into wave optics now. But the same technology that was used for this application, commercialization of defense technology, one of the things that was really cool about this is when light comes through the atmosphere, you've got clouds and stuff going through it, what happens is you don't get a nice, clean, uniform disk of laser light anymore. But if you look at the, the phase of the light, it actually looks like a potato chip. Okay? And the problem with that is when you try to focus a potato chip, a lot of the energy is focused off axis and not where you want it to be. So the idea is to flatten that out. So if you have a wave front that looks like this, how would you flatten that out?
Filter it?
How would you filter it? If I have a wavy surface like this,
Slow it down.
okay, where it's fast, you slow it down. Where it's slow, you speed it up, right? So you basically do the complete opposite. So if you can filter that or reflect it off of a mirror that has the opposite, equal and opposite shape, then where it's delayed, you can equalize that phase front. So this mirror here, this was actually a what they call adaptive optic mirror. And they have, basically it's a mirror that's got a bunch of little actuators on it, we used to call them plungers, that will put a little bit of pressure on certain spots of the mirror. If you can measure this, which you can, there's a device called a Hartman sensor. You can actually measure what that phase profile is, and in real time, send that information to your deformable mirror, so it, as the cloud's going by, you can change the shape of that mirror in real time, flattens out that phase profile, and will take that energy and focus all the way to where it needs to go. This is called a phase conjugate mirror. Ever hear that term, phase conjugation? If you, anybody ever seen that movie, Real Genius? Back in the 80s? Oh my God, old.
The one that was on your first slide?
Yeah, where they shoot the laser beam into the house with the popcorn or blow a hole through the wall in the lab, goes across the campus, and then the grad student comes out and goes, I'm supposed to get the job because I got, look at this mirror, the conjugate mirror you asked for, it's perfect, Phase conjugate mirror, that's what he was talking about. Anyway, so you got to pick up on these little technology bits and pieces.
You see, that's exactly how a telescope works. Looks like that when you put a big dark spot in the middle of all your telescope.
Remember I know the question you're asking, but you have a big dark spot in the middle. But do you? Remember at the beginning of the semester we talked about Poisson's spot? That when you take light and you pass it around an obstacle, because the light bends around that obstacle, it fills in the center area. Same thing.
You're trying to look inside a tiny little telescope. I mean, I know they're big telescopes, but that's still small in the scheme of things.
It fills it in.
Awesome.
Yeah. So, anyways, a little divergent discussion here, got off topic, but it's cool stuff. Stuff that's fascinating. Anyways, let's talk more about mirrors. You got plane mirrors, flat mirrors, concave mirrors, convex mirrors. You also have parabolic mirrors that are used to do things like when they manufacture fiber optic cable. They have this hair-thin fiber that they draw from a draw tower, comes speeding down, several feet per second, and they're spooling it up on the bottom. So, you got this big pumping up on top, and you're drawing it like taffy, and it comes through a bunch of pulleys and wheels and stuff. So it comes in, goes up, goes down like that, and then gets spooled up at the end. But as it's coming down, how do you measure the diameter? This stuff is measured. I have a piece of it in here. This is 125 micron fiber that probably shouldn't have been on the bench there. But, yeah, pass that around. So as that's being manufactured, for you manufacturing people, how do you measure that diameter in real time as it's flying by at, 100 feet per second?
I guess the answer is a laser.
Right. Not only a laser, but a laser with an off-axis parabola. So what they do is you take a parabolic mirror. Okay, a parabolic mirror is kind of looks like this, and you take a mirror that pivots on a point. Okay, laser comes in, bounces off that mirror, strikes this mirror here. As this thing is rotating back and forth really fast, it's going like this, it's going like this, which actually creates a sheet of light that gets projected this way. It's projected that way over the fiber. So imagine, it's going horizontal, this fiber's going this way, so that fiber is going to block off a certain percentage. So if you put a fiber inside here, as it's being manufactured, it's going to create a little hole in that image. And if you take another off-axis parabola, focus this down onto a detector, okay, what happens is you're scanning this beam back and forth, and you're getting this dark spot in the middle. Okay, that dark spot, depending on how much light you're picking up, is directly proportional to the size of this. It's called the laser micrometer. But that uses off-axis parabolic mirrors, and this is what a parabolic mirror will do. Okay, it takes light from a focal point and can collimate it. When you're making a solar hot dog cooker, anybody ever make a solar hot dog cooker? I have one in the back. I had, when I was in 7th grade, I built one in drafting class. My teacher, Mr. Beauregard, in Kiley Middle School, which is junior high school back then, actually had me graphically design, which is kind of a cool thing in itself, create a parabolic surface, and then go into the metal shop, the sheet metal shop, and the wood shop, and make the forms for it, take the sheet metal, bend it around the forms, polish the sheet metal forever, and then stick it out in the sun. But what happens in a parabolic reflector, which is kind of like your satellite dish, a parabolic reflector has a focal point, and light coming in from any point all gets focused to that one spot. So that's the function of the shape. So it doesn't matter where the light strikes it, it all gets sent to one spot. And if you have you make this 3D, that, and you run a rod through the center of this, put a hot dog on it, okay, you can cook it. It actually gets pretty hot. I measured that. It got up to like 230 degrees in like 5 minutes. It was crazy. Back at Kiley Junior High School. So I had one of my students a few years back build one of these here. It's sitting in the back lab. But also build a tracking system that you put it out in the sun, and it'll find the sun and then square itself up, so it tracks as the sun's moving.
What's the difference between a parabolic mirror and a concave mirror again?
Concave, parabolic, you can control where the light comes to focus. In a spherical mirror, okay, the light always comes to focus to one spot. Parabolic mirror, you can direct it to wherever you want, depending on the shape of the parabola. You can create different focal spots.
So concave means it's a sphere.
Well, concave just means it goes in, like swimming pool is concave.
So parabolic mirrors are...
It's a concave mirror,
Okay.
but it's just not spherical. It has a different
It's a
parabola.
subset of
Yeah,
concave.
subset, right. Okay, so, mirrors work by something called specular reflection. When you make a mirror, the smoother the surface is, the more reflective it is. So if you take just a mirror in the bathroom, if you take a piece of glass and coat it with a reflective surface like aluminum, thin sheet, it will reflect. The mirrors that we use in our labs for research and for optics and lasers and such are called front surface mirrors. We'll talk a little bit more in a while about those. But front surface, you have a very flat piece of glass that's highly polished, to optical standards, usually 20th of a wave or better, okay, which takes a lot of time and effort to do. Then you coat that with a reflective surface that, depending on the wavelength that you're trying to reflect, you can find materials that are more reflective at that particular wavelength. But the idea is to have the reflective surface on the front. That way you don't get the double reflection that you would like in a bathroom mirror, where you get a reflection off the front surface and another reflection off the back surface, which is a real pain when you're trying to align an optical system, having two reflective beams. But anyways, if you look at just a flat mirror, okay, in a flat mirror, okay, if you put an object out here on the left side, it will form an image at a distance equal and opposite on the other side. Okay? Magnification will be 1. Okay? Now, if you think about that, why does it do that? How do you know? How can you verify that, validate that? Well, we can use the thin lens equation to show this. What if you had get 1 over d0 plus 1 over f equals 1 over di, right? If you look at the focal length what's the focal length of a flat mirror? If I shine light into that, where is it going to come to focus? It won't, which is another way of saying infinity, right? So a flat mirror is essentially a lens with an infinite focal length. So if you take this thin lens equation, right, and you plug in infinity for the focal length, what's 1 divided by infinity? It's the opposite of infinity divided by 1, or something divided by 0. Okay? Anything divided by infinity is 0. You take any number divided by an infinitely large number, converges to 0. So basically, you're saying that the central portion of that equation, the focal length part of the thin lens equation, goes away. So you have 1 over do is now equal to 1 over di, or do is equal to di. That's where that comes from. And I did that all with my hands. See that? Okay. Assuming it's parallel. Well, this, yeah, yes. Okay, so just a few words about mirrors here. Like I was saying earlier, if you have a back surface mirror, this is what you find in your bathroom. Okay? Piece of glass with a reflective surface on the back. Instant light comes in, you get light that's going to reflect not only off this front surface, remember with the 4% reflection, but also you get the light coming off the back. If you're using this in a laboratory or anything, it will drive you crazy. If I take a laser beam and I shine it on a back surface mirror, you're going to get 2 spots. I mean, because you get the reflective off the back, reflection off the front. Now you get 2 beams of light you have to work with to figure out which one do I want to use, which messes stuff up. Laser mirrors are always front surface, so that you don't get that back reflection. Highly polished piece of glass, you get 1 reflection off the front surface, and then end it. Okay, there's no secondary reflection. So good mirrors are always front surface mirrors, research quality mirrors. Okay, sign convention. And this is the part that kind of screws people up sometimes. When you analyze a reflective system, okay, we still use the Cartesian coordinate system, just like in the lens system. But when light is coming from left to right, okay, when your object is on the left side, okay, just like a lens, okay, distances are negative. But when light strikes that mirror and reflects back, okay, if you formed an image over here in a lens, what would its distance be, positive or negative?
Negative.
Negative. So in a mirror, that now becomes positive. You basically take the right-hand side of the lens, you flip it over to the left-hand side. And as long as you remember that, you'll have no problems figuring this stuff out. Okay? Basically, a better way, same way of saying this here. So light goes in, it actually gets imaged, okay, coming back. So in this case here, if I said, what's the image distance there, would it be positive or negative?
Next on positive. On that side, it will be.
The image
Remember,
distance?
think about a
back
lens.
on the other
Yeah.
side, it would be
Virtual
negative.
Now, if this was a lens, this would be positive, right? And if it's not a lens, it's a mirror, so this is negative. Because behind, you can't reach out and touch this thing. Okay, you can't put a ruler behind your mirror and measure the distance. So if you can't get to it, if you can't project that anywhere, then it's basically a virtual image. Virtual images have negative distances. Okay? If this was curved in one way or another, we can create an image out here, okay, reflects off, comes back. Then you can actually physically project that, you can physically measure that distance will be positive. So if your image is formed on the left, it's positive, it's formed on the right, it's negative. Exactly the opposite of a lens. All right, so let's look at some of the characteristics of concave spherical mirrors. If you have a spherical mirror, they're all kind of the same, okay? Spherical mirror means that it's a portion of a sphere. This is a sphere, okay? It's just the inside portion, it's reflected. If you have a sphere, every sphere has a radius of curvature, okay? If you look at the radius of curvature, this is the radius of curvature, the focal length of the spherical mirror, okay, is always 1/2 the radius of curvature. This is how it works, okay? Light comes like this, it'll come to focus halfway through. So the focal length is equal to, and this again is the opposite of a lens, okay? For a negative lens, for a concave lens, okay, what's the focal point of a concave lens, positive or negative? If you have a lens that looks like this, it's going to be negative, right? In mirrors, that's called a positive, okay? So the focal length of a concave mirror is the opposite of that of a concave lens. It's going to have a positive focal length, and that focal length is going to be the radius of curvature divided by 2. Let me skip over this for a second. This is just a ray tracing version of that. But I mean, if you can do a ray tracing also of a concave mirror. This shows that if I put an object out here somewhere, and this is the focal point, okay, light's going to come in, reflect off the mirror, form a real image to the left of the mirror. Okay? Depending on where this object is, according to the thin lens equation, it's going to determine what the size of this is. So again, a concave mirror does exactly the same thing as a negative mirror, essentially. It's the opposite of a negative lens. If I also take that object and move it inside the focal point, okay, you end up getting the same image you would for as a lens. You get a virtual image. Okay? Think lens. You move the object inside the focal point, I end up getting a virtual image, which is a magnifying glass. You have to look through the lens from the other side to see the magnified image. Same thing for a mirror. If I take the object and move it in between the focal point and the mirror, I end up with a virtual image, a magnified image, and this is the bathroom mirror that lets you see the hair on your nose. So this is what you're looking at. Now you put your face inside the focal point, and then you look at the hair on your nose, which is the image that's on the other side. And your big pores. Wrinkles.
Is that something like they use for solar towers, or for, like, have you heard of a solar tower?
Solar towers, yeah.
They have them, I think, in Spain, where they have this massive tower and there's a ton
Collects
of
the light.
mirrors.
Yeah, collects the light and focuses
Yeah.
it onto either like a heating element or a detector.
Yeah,
or
to
some
create
sort. Yeah.
electricity.
Yeah.
I was just curious.
Those are more likely parabolic mirrors, because the parabolic mirrors are better for collecting light and refocusing it.
Oh.
So, but this is, again, this is in reflecting mode. This is a mirror that you would use as a magnifying mirror. Let's see. I know we fixed this Java applet, and we cross our fingers every time.
Hopefully this time it'll work right.
Because we opened this the other day. Right? Yes, okay. So you remember this applet, virtual optics bench? You can also use this for mirrors. I can put a mirror anywhere I want. Okay, change its radius of curvature. I can take an object, and this again, for a sanity check, if you're like, I'm not sure where the image is going to be formed. If I put an object, okay, if I change the size of the object, its position, it'll tell you where that image is going to be formed. Pretty cool. If I move it inside the focal point, boom, it becomes a virtual image. Back out. So use this as a tool. I mean, it's there for you. It's free, which is a good thing. You can also make this a positive mirror. Okay. If I take my object, remember, objects seem smaller than they are or closer. Objects are closer than they appear in the mirror. Okay. Look what happens if I have an object way back there. the image is tiny. Okay? If I move closer and closer, it gets a little bigger, but still, it's smaller. It always has a magnification that is less than this thing. So, no matter how close you get. It's impossible to have your image, well, I guess it's not impossible if you're projecting it from something else, but impossible to have an image on this side, I'm sorry, an object on this side because you're inside the mirror now. Okay, unless you're, it's the story. Alice, yeah, Alice in Wonderland, yeah, the looking glass. So anyway, so you can see that the image can be smaller for a positive mirror. Okay. So let's take a look at one. So this is a convex spherical mirror as opposed to a concave spherical mirror. Same deal as a negative mirror. This mirror here, okay, has a focal point that is on the right side. Okay, so if you look at the radius of curvature of this mirror, same as a negative mirror, okay, the focal point is always going to be 1/2 the radius of curvature. So the focal point's in here. But because mirrors are the opposite of lenses, okay, for a positive mirror, okay, the focal length is negative. Negative focal length means that focal length is inside the mirror. It's a virtual focal point. Okay, so this is also called a diverging mirror, okay, similar to like a divergent lens. So this is kind of what's happening in there. You put an object to the left, forms a smaller image inside the mirror, and that's what you see in your side view mirror. So let's look at the mirror equation, which is strikingly similar to the thin lens equation, isn't it? Okay. So the magnification, same exact thing, image distance divided by object distance. So for example, let's say we place a 25 centimeter object in front of a concave spherical mirror with a plus 15 centimeter focal length. Find the location and size of the image. Okay. Well, you've got your mirror, it's got a 15 centimeter focal point, you got a 25 centimeter object distance. Where's the image going to be formed? If we look at our thin lens equation, okay, the left side is exactly the same. So we have 1 over d0 plus 1 over f equals 1 over di. 25 centimeters is negative because it's to the left of the mirror. Okay. Because this is a negative mirror, it has a positive focal length. Okay, so we have 1 over plus 15 for the focal length is equal to 1 over di. We calculate what the image distance is. It's 37.5 centimeters, positive 37.5 centimeters. So where is that going to be formed? To the left or to the right of the mirror? Who says left? Who says right? Left. Remember, think lens and then do the opposite. So if you look at this, if it was a lens, the image would be placed over here, but because it's not a lens, the mirror, it's over here, 37.5 centimeters away. So this is where your image will be formed. To determine whether it is inverted or upright, you look at the magnification. Image distance divided by object distance, 37.5 divided by negative 25 gives you minus 1.5. Okay, so you have an image that is formed to the left of the mirror, inverted because this is negative, and it's 1.5 times larger than the original object. Good? Straightforward? All right. For the last activity, I want you guys to do this one. Okay, in the last 5 minutes of class. Let's say we have that object placed 15 centimeters. So basically it's the same problem, except we've taken that object and moved it now inside the focal point. So tell me where the image is going to be and how big is it going to be. Positive or negative?
Opposite side of.
Yeah, if it was positive, that means it's a real image on the left side. Right. Who else got something? Anybody else got a number? Alex?
I got a negative 38.46.
Okay, sanity check, without even thinking about the numbers, which one makes more sense?
The plus 9.
Forget the number, just positive or negative?
Negative.
Negative, why?
Inside of the middle.
Because you're inside the focal point. Yeah, you're inside the focal point, it's gonna give you a virtual image. In a mirror, virtual image is behind the mirror, which has a negative distance. So the negative one is correct.
Okay.
I can't tell you about the number, I haven't done it yet, but at least from a sanity standpoint, you know that's gonna be correct. If you got a positive number, then you probably did something wrong. All right, so let's do this one. So we take our thin lens equation, which is now our mirror equation, okay? 1 over d0 plus 1 over f is equal to 1 over di, okay? 1 over minus 15 centimeters plus 1 over, okay, it's a negative mirror, so it has a positive focal point, 25 centimeters is equal to 1 over di. Calculate di for this,
0.026.
0.026.
That's before
That's
inverting.
before inverting.
Oh, so it's negative 38.
Negative 38.46, all right.
I
Let me
got
check this out.
37.5.
Yeah,
I got negative 37.5.
Why is it only being the same positive here?
I got minus
Here.
37.5. I'm gonna be right.
Yep.
So
Yeah,
minus
I think you just-
37.5.
All right, yeah, I see mine.
What?
I feel better again, better, the right
You're
answer.
not bringing up P.
Right.
All right.
So
It's
minus,
just putting the negative.
right. So if it's minus 37.5, okay, what's the magnification?
Oh.
Di divided by do.
My current paper strength.
Okay.
Yeah.
Minus 37.5 divided by minus 15 centimeters.
But it's like point.
Okay, minus divided by a minus gives you plus.
Yeah, if you
Okay,
put it.
so
So
that
it's right here.
divided by
Yeah.
equals minus, which is equal to 2.5 plus. So we have a magnification of 2.5. So we've got this image now that's formed to the right, 37.5 centimeters. So if this is 25, 37.5 is going to be inside my equation here. Okay, so it's going to be over here somewhere. And it's going to be 2.5 times what the original size was. So this here is now 37.5 centimeters because it's minus, it's virtual, which means if you want to see this, okay, if this is your face, okay, looking into this mirror, okay, what you're going to see is a magnified version of whatever you're looking at.
So the 37, how, when you measure that, this one is from the normal.
Right. Yes, yeah, it's from the normal, correct. Okay, so kind of went a couple minutes over there, but when we get back together on Thursday, okay, we'll do a couple more examples, okay, with the positive mirrors, okay, do a classroom activity, and I'll probably have a short quiz on mirrors on Thursday, because I would rather give it to you in class. That should take 15 minutes of class. So on Thursday, I'll give you an in-class quiz of the rest of the class to finish it. That way you can go on spring break, for those who've done a lab on Thursday, without anything hanging over your head. When we get back, however, the week that we get back, we should probably think about having an exam, first exam. We'll probably have a review on that Tuesday. We'll probably give you a take-home exam on that Thursday, and we'll do the following Tuesday. Sound like a plan? All right. Before you leave, here's a simple little quiz that's due on Thursday. This has to do with the lens maker's equation and simple thin lens equation. Hope you enjoy it. For those of you up lab today, you'll be back here in 10 minutes. Take a break.